In the autumn of 1993, a team of archaeologists were working a site near the village of Nemelany in the Moravia region of the Czech Republic. They were excavating a 9th century grave, a simple affair belonging to what they presumed was a warrior of some local importance. The soil was damp and heavy. The work was slow. They found the usual things at first. A few pottery shards, the corroded metal of a shield boss, the dark outlines of a human skeleton. And then they found the sword. It was heavily rusted, a long, slender shape, locked in a mass of earth and corrosion. It was a significant find, of course. Any sword from this period is. They carefully documented its position, lifted it in a block of soil, and sent it back to the lab for conservation and analysis. For months, the sword was just another artifact, another piece of the puzzle of 9th century Moravia. The conservators painstakingly worked to remove the centuries of rust and grime, revealing the blade beneath. It was a good sword, well proportioned. Along the upper part of the blade, near the hilt, they found a faint inscription inlaid in a different metal. The letters were clear plus Viperplut. The archaeologists were excited. This was an Ulfberht sword, a famous type known for its quality, associated with the Vikings and the Frankish Empire. It was a prestigious weapon, and finding one this far east was unusual. But the real shock came later. As part of the analysis, a small sample of the blade was sent for metallurgical testing. The team expected to see the typical structure of a high-quality European sword of the era. That meant bloomery iron folded and hammered over and over again to work out impurities and distribute the carbon. It was a laborious process that always left behind small, elongated pockets of slag, glassy impurities trapped within the metal. It was the signature of European ironwork for 1,000 years, but the report that came back from the lab made no sense. The scientists ran the tests again. The results were the same. The Nemelany sword contained almost no slag. Its internal structure was clean, uniform. The carbon content was high, around 0.75%, and it was distributed with a consistency that was simply not possible with a bloomery forge. The material was crucible steel. To make steel like this, you had to seal iron and carbon sources in a clay crucible, heat it until the iron melted into a liquid, and let the carbon dissolve into it. This process, which burns away impurities as slag, was not known in Europe at the time. It was a technology of Central Asia, of Persia, and India. The steel in this 9th century Moravian grave, held in the hands of a long-dead warrior, was not from Europe. Its raw materials had been smelted and forged into an ingot in a workshop perhaps 2,000 miles away, somewhere near the Amu Darya River. It had traveled up the Volga trade route, passed through the hands of Rus's merchants, and found its way to a smith on the Rhine River, who then forged it into one of the most advanced weapons on the planet. The Nemelany sword was not just a weapon. It was a mystery. It was a piece of high technology found centuries before it was supposed to exist in Europe. It told a story of a lost world of incredible craftsmanship and long-distance trade, and it forced everyone to ask a new question. How did they do it? Number 15, the brand name was a promise. In 1889, a Norwegian archaeologist named Anders Lorange published a book called Den Yngre Jernalders Sverd, or The Swords of the Younger Iron Age. Lorange was a methodical man. He spent years traveling across Norway, visiting museums and private collections, documenting every Viking Age sword he could find. He measured them, sketched their hilts, and paid special attention to any marks or inscriptions on the blades. And he began to notice a pattern. On a significant number of the finest, best-preserved swords, he found the same name inlaid into the blade with twisted iron rods. The name was Velpert. Lorange was the first to properly categorize these swords. He didn't know what the name meant exactly. He speculated it was the name of a famous swordsmith, a single master craftsman whose work was sought after across the known world. For almost a century, that was the prevailing theory. But as more and more of these swords were found, from Ireland to Russia, the theory started to fray. Over 170 Ulfberht swords have been found to date. The dates of their burial span from the 9th to the early 11th century. That's a period of nearly 200 years. It was too long for a single man's working life. The inscription itself was the next clue. It was almost always spelled in all capital Latin letters, Ulfberht++. The crosses at the beginning and end were significant. In a largely illiterate world, symbols carried huge weight. The cross was a powerful Christian symbol, which was interesting because the swords were overwhelmingly used and buried by pagan Norsemen. The name Ulfberht is Frankish or German in origin. This placed the workshop not in Viking Scandinavia, but somewhere in the Rhine River Valley in what is now Germany. This was the heartland of the Carolingian Empire, the great Christian power of the age. The current understanding is that Ulfberht was not a single person. It was the name of a workshop, or perhaps a series of workshops controlled by a single authority, maybe a monastery or a powerful bishop. Monasteries in the Frankish Empire were centers of technology and industry. They had the resources, the organization, and the permanence to maintain a complex manufacturing process for generations. The name Ulfberht became a trademark, a brand name. And like any powerful brand name, it was a promise of quality. When a Viking chieftain or a wealthy warrior bought a sword marked with the Ulfberht name, he wasn't just buying a sharp piece of metal. He was buying a reputation. He was buying the best. The name guaranteed that the sword was made from superior steel, that it was properly heat-treated, that it was balanced, strong, and flexible. It was the 9th century equivalent of a Ferrari or a Rolex. It conveyed status. It told everyone on the battlefield that its owner was a man of wealth and taste, and that his weapon would not fail him. The inscription was the first secret. It was the visible sign of all the invisible technology and skill that went into the sword's creation. It was a simple name, hammered into the steel, but it carried the weight of an entire industrial and cultural legacy. Number 14, the best swords had fakes. In the early 2000s, Dr. Alan Williams, an archaeometallurgist at the Wallace Collection in London, began a detailed study of the Ulfberht swords. He was a quiet, meticulous scientist, a man who preferred the story told by steel's microstructure to the grand tales of sagas. With permission from various European museums, he was able to take tiny pin-prick samples from a number of blades for analysis, and he sorted the swords into two groups based on the spelling of the inscription. The first group had the high-quality inscription, Flibber+. The second group had a slightly different, more variable spelling, often Ulfberht with a cross only at the beginning, or other minor variations. When the results came back from the lab, they revealed a stunning act of ancient industrial espionage. Every single sword from the first group, the ones with the precise Ulfberht spelling, was made from high-carbon crucible steel. They were the genuine articles, the super swords of the Viking Age. Every sword from the second group, the ones with the slightly off spelling, was made from traditional, inferior, pattern-welded steel. They were fakes, they were knockoffs, made by less skilled smiths, trying to cash in on the famous Ulfberht brand name. Imagine a Viking trader in the port of Hedeby in Denmark around the year 950. He's looking to buy a new sword. Two smiths have stalls set up. The first smith, a Frankish merchant with connections, has a real Ulfberht. The blade has a dark, uniform sheen. The inscription is sharp and clear. He lets the Viking handle it. It feels alive, light, but powerful. The price is astronomical. It costs a fortune in silver, furs, or slaves. At the next stall, a local smith has his own swords for sale. They look similar. He's even tried to copy the famous name, inlaying it into the blade. But maybe his literacy isn't perfect. He spells it Ulfberht+T, missing the initial cross, or maybe he just can't quite replicate the masterful inlay of the original. His blade is pattern welded. You can see the faint watery lines on the surface where he's twisted and forged different grades of iron together. It's a good sword, better than most, but it's not an Ulfberht. It will bend in a hard fight. Its edge won't hold as long. The price is much lower. The existence of these counterfeits tells us something important. It tells us that the superiority of the real Ulfberht swords was not a secret. Everyone, from the warriors who used them to the smiths who tried to copy them, knew that there was something special about a genuine Ulfberht blade. They might not have known why. They wouldn't have understood the chemistry of crucible steel or the physics of heat treatment. But they knew the results. They knew that one sword would shatter a shield and keep its edge, while the other might chip or break on a helmet. The fakes were not just a commercial scam. They were a testament to the power of the original. You only counterfeit something that is immensely valuable. The forgeries prove that the Ulfberht wasn't just a good sword. It was the standard by which all other swords were judged, and a standard so high that many were willing to cheat to be associated with it. Number 13, the steel traveled thousands of miles. Ahmed ibn Fadlan was a 10th century Arab traveler and writer. In 921, he was sent by the Caliph of Baghdad on a diplomatic mission to the king of the Volga Bulgars. Along his journey, he encountered a group of Norse traders on the Volga River, whom he called the Ruses. His detailed and often horrified account of their customs provides one of the few written eyewitness descriptions of the people we call Vikings. He described their hygiene or lack thereof, their funeral rituals, and their appearance. He also described them as master traders. His account gives us a window into the world that brought the Ulfberht sword into being. The secret of the Ulfberht steel wasn't just in a European workshop, it was in the vast, interconnected trade network that spanned continents. This network was the Volga trade route. It was a riverine superhighway that connected Scandinavia to the Caspian Sea and the lands of the Abbasid Caliphate. The Rus were the masters of this route, starting from their bases in places like Staraya Ladoga. They would load their longships with the goods of the north: honey, wax, amber, high-quality furs from squirrels and Arctic foxes, and slaves captured in the Slavic lands. They sailed and rowed down the rivers and lakes of what is now Russia, making arduous portages, dragging their ships overland between watersheds. Eventually, they reached the Volga River, which took them south to the Caspian Sea. There, in cities like Itil, the capital of the Khazar Khaganate, they met merchants from the south. Arab and Persian traders brought silver dirhams, silk, spices, and other luxuries of the Islamic world. The Ruses traded their northern goods for this southern wealth, but they also traded for one very specific, very valuable industrial commodity: cakes of crucible steel. This steel, which Arabs called falad and is often known by the Indian name woots, was made in workshops in places like Merv in modern-day Turkmenistan or in parts of India. It was a material completely unknown to European smiths. The Russ's merchants would acquire these ingots, small round cakes of ultra-high carbon steel, and add them to their cargo for the long journey home. From the Volga, the steel would travel west, through a series of other trade routes, until it reached the Rhine River Valley. There, in the Frankish workshops, the master smiths of the Ulfberht clan would buy this exotic, expensive material. This trade route was the sword's lifeline. The smiths on the Rhine likely had no idea where the steel came from precisely. They just knew that merchants from the east could supply them with a metal that was far superior to anything they could produce locally. It was a fragile connection. The route depended on a delicate balance of power between the Ruses, the Khazars, the Volga Bulgars, and the Caliphate. When that balance shifted in the 11th century, when new nomadic groups swept across the steppes and the trade routes were disrupted, the supply of crucible steel to Europe dried up. And soon after, the production of Ulfberht swords stopped. The secret wasn't forgotten. The key ingredient just stopped arriving. Number 12. It started as a small, ugly cake of steel. Let's travel to Central Asia, perhaps to the city of Merv around the year 850. In a dusty courtyard, a master smith is preparing for a steel run. He doesn't think of it in terms of chemistry. To him, it is a near magical art, a secret process passed down from master to apprentice. He starts not with a forge, but with a small clay pot, a crucible. Inside this crucible, he places a specific mixture of ingredients. And there is soft, spongy iron smelted at a low temperature to keep it pure. There are carefully selected leaves, woods, or other sources of carbon. Sometimes he adds a bit of broken glass. The glass will melt and form a liquid layer on top, sealing the mixture from the air. He carefully seals the crucible, making it airtight. Then he and his assistants place it, along with dozens of others, into a large furnace. For days, they will feed the furnace with charcoal, using bellows to force the temperature higher and higher, far hotter than a typical European bloomery forge could ever get. The smith judges the heat by the color of the flame and the glow from the cracks in the furnace. He needs to reach a temperature of around 1300 degrees Celsius. At this heat, inside the sealed crucible, something incredible happens. The iron doesn't just get red hot, it melts. It turns into a liquid. As a liquid, it can absorb the carbon from the leaves and wood directly, dissolving it completely and evenly throughout the molten metal. The impurities, the slag, separate out, either absorbed by the glassy layer on top or pushed to the sides. After several days, the furnace is allowed to cool, a process that must be done slowly and carefully. When the crucibles are finally cool enough to handle, the smith breaks them open. Inside each one is not a lump of spongy iron, but a small, solid cake of steel. It is roughly the size of a hockey puck, with a rough, crystalline surface. This is the Wootz ingot. This small, unprepossessing object is the raw material for the Ulfberht sword. It is a near-perfect steel alloy. It is free of slag. Its carbon content is high and uniformly distributed. When a Roos's trader bought these ingots, he was buying potential energy. He was buying a material that was, at a microscopic level, fundamentally different from European steel. The European bloomery iron was made by heating iron ore with charcoal until it formed a spongy mass, or bloom. This bloom never fully melted. It was a mix of iron, steel of varying carbon content, and a great deal of slag. The European smith's entire job was to try and purify this messy material by hammering, folding, and welding it together, a process that could never get rid of all the slag. The smith in Merv had bypassed that entire problem. By melting the iron in a controlled, oxygen-free environment, he had created a perfect starting material. The hard work wasn't in the forging, it was in the initial creation of the steel itself. The ugly little cake of steel was the secret ingredient, a piece of industrial magic from another world. Number 11, the smith was fighting the steel's memory. A master smith in a workshop near Mainz on the Rhine River receives a shipment of the eastern ingots. It is the year 900, he has paid a high price for them, he knows their value. He also knows their difficulty. Working with this crucible steel is unlike working with the local bloomery iron he is used to. The ingot has a memory of how it was made. As the molten steel in the crucible cooled down, the carbon and iron atoms arranged themselves into a rigid, crystalline structure. Large, tree-like crystals of a compound called cementite, an iron carbide, formed throughout the ingot. This structure makes the steel incredibly hard, but also very brittle. If the smith were to heat it up and hit it with a hammer, it would likely shatter like glass. His first and most difficult task is to break this memory. He cannot simply forge it into a sword shape. He has to transform the steel on a microscopic level. The process is called thermomechanical working. He carefully heats the ingot in his forge. He must be extremely careful with the temperature. If he gets it too hot, he will burn the precious carbon out of the steel, ruining it. If it's too cool, it will be too brittle to work. He heats it to a specific orange-yellow color, then brings it to the anvil. He doesn't strike it hard. He uses a series of light, rapid hammer blows. He is not trying to shape the steel yet. He is trying to break down the large cementite crystals. With each cycle of heating and hammering, those large, brittle crystals are fractured and reformed into much smaller, more evenly distributed particles. He has to work the ingot slowly, patiently, from every direction. It is a long, arduous process. He is essentially fighting the steel, forcing it to forget its crystalline past and accept a new, more uniform internal structure. After many hours or even days of this careful work, the ingot has been transformed into a workable bar of steel. The carbon is now distributed not as large crystals, but as tiny microscopic spheres within the iron matrix. The steel is now no longer brittle. It is tough and resilient. Only now can he begin the actual process of forging the sword blade. He will heat and hammer the bar, drawing it out into the long, tapering shape of the blade. This process further refines the grain structure. The tiny particles of cementite are elongated and aligned along the length of the blade. This is what gives the Ulfberht its legendary combination of properties. The hard cementite particles provide the wear resistance needed for a sharp edge, while the tough iron matrix provides the flexibility to absorb the shock of a blow. The smith on the Rhine was more than just a blacksmith. He was a practical metallurgist. He may not have had the words to describe what he was doing, but he understood the process. He knew how to take a difficult, exotic material and, through sheer skill and patience, tame it and transform it into the blade of a super sword. Number 10, carbon was the magic ingredient, but only the right amount. In the 1980s, before Dr. Williams' more comprehensive work, a team of researchers at the British Museum were analyzing the blade of an Ulfberht sword found in the Thames River. They used a technique called electron microscopy to look at the internal structure of the steel in incredible detail. What they found confirmed the uniqueness of the material, but the most important number they identified was the carbon content. It was approximately 0.75%. To the layman, that number is meaningless. To a metallurgist, it is perfect. Carbon is the single most important element in steel. Pure iron is soft, you can bend it easily, it won't hold an edge. Adding a small amount of carbon to iron dramatically changes its properties. The carbon atoms, which are much smaller than the iron atoms, fit into the crystalline structure of the iron, distorting it and making it much harder for the iron atoms to slip past one another. This makes the material harder and stronger, but it's a delicate balancing act. A sword made with low carbon steel, say 0.2%, would be tough. It wouldn't break, but it would be too soft. Its edge would dull quickly and the whole blade could bend and stay bent after a powerful blow. This was the problem with most average quality swords of the Viking Age. They were reliable in that they wouldn't shatter, but they needed constant maintenance and lacked real cutting power. On the other end of the scale, if you have too much carbon, say 1.5% or more, you get cast iron. The steel becomes incredibly hard, but also extremely brittle. A sword made of cast iron would hold a razor edge, but it would shatter into a dozen pieces the first time it struck another sword or a shield. It would be completely useless as a weapon. The sweet spot for a sword, the ideal balance between hardness and toughness, lies in a narrow window. The Ulfberht smiths, using crucible steel, were able to hit that window with astonishing precision. Their steel had a carbon content of around 0.75%. This is what is known as a eutectoid steel. It was high enough in carbon to be hardened to a phenomenal degree, allowing it to take and hold a terrifyingly sharp edge. Yet it was not so high in carbon that it became brittle. When combined with the proper heat treatment, this specific carbon content allowed the sword to flex under stress and return to absorb the shock of impact without breaking, and to cut through mail and bone. This level of precision was impossible to achieve with a European bloomery forge. The bloomery process was chaotic. The carbon content varied wildly throughout the bloom. A smith could only try to average it out by folding and welding. He could never be sure of the final carbon percentage. The crucible process, however, was like a chemical recipe. By using a precise amount of iron and carbon sources in a sealed container, the makers of the Wootz ingots could produce steel with a consistent and ideal carbon content every single time. The magic was in that number 0.75%. Number 9. They baked out the impurities. A typical Scandinavian blacksmith, let's call him Einar, stands before his forge in Birka, Sweden, in the year 920. He is making a sword for a local chieftain. His raw material is a bloom of iron, which he made himself. He built a small chimney-like furnace of clay and stone, layered it with charcoal and bog iron ore, and spent the better part of a day pumping a set of bellows. The result was a spongy, misshapen lump of iron riddled with bits of charcoal, sand, and other melted rock. This impurity is slag. Einar's entire process now is a battle against the slag. He heats the bloom in his forge until it's glowing hot, then hammers it on the anvil. With every blow, liquid slag squirts out from the metal. He has to cut, fold, and hammer weld the iron back on itself over and over and over again. Each fold helps to squeeze out more slag and even out the carbon content. After days of this brutal, repetitive labor, he has a bar of iron that is reasonably clean. But it is never perfect. If he were to polish a cross-section of his finished sword blade and look at it under a microscope, he would see long, stringy inclusions of slag trapped within the steel. These slag inclusions are weak points. They are internal fault lines. Under the stress of a hard blow, a crack can start at one of these inclusions, causing the blade to snap. Now, travel south to the Rhine. A smith named Gerolf is working in the Ulfberht workshop. His raw material is not a bloom, but a cake of crucible steel. The process that created his steel has already done the hard work of purification for him. Inside the sealed crucible, when the iron became liquid, the lighter slag impurities floated to the surface, where they were trapped in the molten glass layer. The heavy, pure iron-carbon alloy sank to the bottom. When the ingot cooled, it was an almost perfectly clean and homogeneous piece of metal. Gerolf's job is not to purify the steel, but to shape it. He still has to forge it with immense skill, but he doesn't have to fight against the material's inherent flaws. The absence of slag means his final blade is metallurgically clean. It has a uniform internal structure, free from the weak points that plague Einar's sword. This is why an Ulfberht sword could be made thinner and lighter than a typical pattern-welded sword, yet be significantly stronger. The integrity of the material itself was on a completely different level. It could withstand stresses that would cause a slag-ridden blade to fail. The baking process in the crucible, thousands of miles away, removed the sword's original sin, the impurities that weakened all other European blades. This internal purity was an invisible secret, but it was perhaps the most important one of all. Number 8. The blade was both hard and soft. The final shape of the Ulfberht sword has been forged. The fuller has been added, the edges have been defined. It has been normalized, a process of gentle heating and cooling to relieve the stresses of the forging process. Now, the smith faces the most critical and dangerous stage of the entire process, the series of steps that will turn the blade from a well-shaped piece of soft steel into a truly legendary weapon. This is the heat treatment. The goal is to make the blade hard where it needs to be hard, and soft where it needs to be soft. An ideal sword needs two contradictory properties. The edge needs to be extremely hard. Hardness allows it to be sharpened to a razor-fine angle and to resist dulling and chipping when it cuts. The body and spine of the sword, however, need to be softer and more flexible. This property, called toughness, allows the blade to absorb the immense shock of striking a shield or another sword without shattering. A blade that is uniformly hard all the way through would be a fragile, dangerous weapon. The Ulfberht smiths were masters of what is called differential hardening. There are several ways they could have achieved this. One method is to insulate the spine of the blade with clay before heating and quenching. The clay layer would cause the spine to cool more slowly than the exposed edge. This would result in a super hard edge and a softer, tougher spine. Another possibility is that they used an interrupted quench. The smith would heat the entire blade to the critical temperature, a specific cherry red color he judged by eye in the dim light of his forge. He would then plunge it into the quenching tank of water or oil for only a few seconds. This would be just long enough for the thin edges to cool rapidly and become fully hard. He would then pull the blade out, allowing the residual heat, still trapped in the thick spine, to flow back towards the edges, gently softening them and the rest of the blade. This process transforms the steel at an atomic level. When the edge cools rapidly, the iron and carbon atoms are frozen in a chaotic, stressed structure called martensite. This martensite is incredibly hard and brittle. When the spine cools more slowly, the atoms have time to arrange themselves into a more stable, layered structure of ferrite and cementite called perlite. Perlite is much softer and tougher. By controlling the heat and the cooling, the smith could create a composite structure within a single piece of steel. The finished blade would have a skin of hard martensite along its cutting edges, wrapped around a core of tough perlite. It was the perfect combination. The hard edge could shear through mail rings and flesh, while the tough body could flex and absorb the brutal reality of combat. This dual nature, this engineered contradiction of being both hard and soft at the same time, was a product of immense skill and knowledge. Number 7. The quench was a moment of truth or failure. The sword is ready. It glows a uniform, vibrant cherry red in the twilight of the forge. The smith, his face slick with sweat, lifts it from the coals. He has only seconds. The temperature is perfect, somewhere around 800 degrees Celsius. In these few moments, everything can be lost. He moves with a calm, practiced speed to the quenching trough, a long wooden tub filled with water, brine, or perhaps oil. This is the quench. It is the most dramatic and violent part of the sword's birth. He plunges the blade into the liquid, tip first and perfectly vertical. The sound is explosive. A violent hiss and a roar of steam erupt from the trough, filling the workshop with a thick, white cloud. The water around the blade instantly boils, forming a vapor jacket that insulates the steel. This is a dangerous phase. He might move the blade slightly to break this jacket and ensure even cooling. He holds it steady, feeling the vibrations through the tang. This is the moment of transformation. The rapid cooling, thousands of degrees in seconds, is trapping the steel's atomic structure in the hard, brittle martensitic state. This is also the moment of maximum risk. The stresses on the steel are immense. If there was any tiny unseen flaw in the forging, a microscopic crack, the thermal shock of the quench will cause it to propagate catastrophically. The blade could shatter, exploding with a sharp crack, or it could warp, twisting into a useless corkscrew shape. Or it could survive the quench, but have a network of tiny stress fractures that will cause it to fail in its first battle. All the days of forging, all the expense of the precious crucible steel could be turned to scrap in a single heart-stopping second. The smith feels it through his hands. The vibrations die down, the hissing subsides. After a specific count, a length of time known only to him through years of experience, he pulls the blade from the trough. It is dark, covered in a black scale. He taps it gently, it rings with a high, clear note. It survived. He holds it up, sighting down the length to check for any warps. It is true. The blade is now in its hardest possible state. It is as brittle as glass. If he were to drop it on the stone floor, it would likely shatter. It is not yet a sword. It is a sword-shaped piece of extreme hardness, holding an incredible amount of internal stress. But the most dangerous moment has passed. The quench has locked in the potential for greatness. The next step will be to tame that brittle hardness and bring forth the flexibility that lies dormant within the steel. Number 6, the fire that followed the water. The smith lays the quenched blade on a bed of cool coals. It is dark, hard, and brittle. It is full of stress. He now has to perform the second half of the heat treatment, a delicate and beautiful process called tempering. If quenching is a violent shock, tempering is a gentle persuasion. He cannot put the blade back into the main forge, the heat is too intense. Instead, he will use a slow, gentle heat to carefully reheat the blade. Before he does this, he takes a stone and polishes a small section of the blade until it is bright and silvery. This polished patch will be his thermometer. He gently wafts the blade over a low flame or pushes hot embers up against the spine. He is not trying to make the blade glow. He is aiming for a much lower temperature, perhaps only 200 to 300 degrees Celsius. He watches the polished patch of steel with the focus of a hawk. As the steel heats up, a thin layer of oxide forms on the surface. The thickness of this layer determines how it refracts light, creating a predictable series of colors. This is his guide. First, the polished steel will turn a faint, pale straw yellow. This indicates a temperature of around 220 degrees Celsius. At this temperature, the blade would be extremely hard, suitable for a razor, but still too brittle for a sword. As the heat creeps higher, the color deepens to a rich, dark straw, then to a brown or bronze color. Now it's getting warmer, the internal stresses are beginning to be relieved, the toughness is increasing, but he is sacrificing a little bit of the extreme hardness. Then the colors shift to purple and finally to a deep blue. A blue temper would make the blade very tough and flexible, like a spring, but it would be too soft to hold a sharp edge. The smith is looking for a specific color. He wants a dark straw or a bronze brown on the edge of the blade. This will give him the perfect balance. It will relieve enough of the stress to make the blade tough and resilient, but it will leave the edge hard enough to be exceptionally sharp. He might even control the heat so that the spine of the blade gets hotter, reaching a blue or purple temper, making it even more flexible than the edge. He watches the colors run across the steel like a sunrise. When the bronze color reaches the edge, he pulls the blade away from the heat instantly and lets it cool in the air. The process is complete. The fire has followed the water, the tempering has transformed the brittle, stressed martensite from the quench into a tougher, more stable structure called tempered martensite. The smith has traded a small amount of unnecessary hardness for a huge gain in toughness. The blade is now both very hard and very flexible. It will ring like a bell when struck, it will bend in an arc and spring back to true. It now has the soul of a sword. This delicate dance of colors, this precise application of low heat, is what unlocks the full potential of the high-carbon crucible steel. Number 5. The groove was for weight, not blood. For centuries, the shallow groove running down the center of many medieval sword blades was called a blood groove, or blood gutter. The myth was that its purpose was to channel the blood of a vanquished foe away from the hilt, or to allow air to enter a wound to prevent suction. This is pure fantasy, a Gothic invention of the 19th century. The real purpose of this feature, known correctly as a fuller, is a masterpiece of engineering. Its secret is not in biology, but in physics. The Ulfberht smiths were not just metallurgists, they were structural engineers. Consider a simple, flat steel bar. To make it stiffer, you have two options. You can make it thicker, which adds a lot of weight, or you can change its shape. Think of a modern I-beam used in construction. It has a thin, central web and two wide flanges at the top and bottom. This I-beam shape is incredibly rigid and strong for its weight, far more so than a solid square bar of the same mass. The fuller on a sword blade works on the exact same principle. By forging or grinding a channel down the middle of the blade, the smith creates a cross-section that is effectively a double I-beam. This has two immediate benefits. First, it removes material from the center of the blade, where it contributes little to the blade's stiffness. This makes the sword significantly lighter. A lighter sword is a faster sword. It can be started, stopped, and changed in direction with much less effort. In a fight where a fraction of a second matters, this speed and agility are life-saving advantages. A warrior with a well-fullered blade could deliver several cuts in the time it took a man with a heavier, clumsier sword to deliver one. Second, the I-beam geometry actually makes the blade stiffer and stronger in relation to its weight. The two raised ridges on either side of the fuller act like the flanges of the I-beam resisting bending forces. This allowed the Ulfberht smiths to forge a blade that was wide for effective cutting, but also light and rigid. It would not wobble or flex uncontrollably on impact. It would track true and deliver the full force of the blow to the target. Creating a perfect fuller was a sign of immense skill. It had to be perfectly centered and uniform along the length of the blade. If it was off-center, it would create a weak spot and could cause the blade to warp during the heat treatment. Forging a fuller was a difficult process requiring specialized tools called swadges to shape the hot metal. Some may have been created by grinding after the main forging was complete, a laborious task with the simple abrasives of the time. However, it was done. The fuller was a deliberate and sophisticated design choice. It was a secret to making a sword that felt like a part of the warrior's own arm, fast, responsive, and deceptively strong. Number 4. The sword tapered in two directions. A modern visitor to a museum, perhaps the National Museum of Finland in Helsinki, is given the rare opportunity to handle a real Ulfberht sword. The curator lays it on a velvet cloth. The visitor expects it to be heavy, a brutish piece of iron, but when he picks it up, he is shocked. It feels impossibly light, almost alive. It seems to float in his hands, the point easy to direct. It does not feel like the 1.2 kilogram object the museum label claims it is. The secret to this feeling is not just the fuller, it is in the blade's complex geometry, specifically its taper. The Ulfberht sword tapers in two directions at once. The first is the profile taper. When you look at the blade flat, you can see that it is wider at the hilt and gradually narrows towards the tip. This shape puts more of the mass and cutting surface closer to the hand, making it a powerful slicing weapon, while the narrow point is still effective for thrusting. The second, and more important, taper is the distal taper. This refers to the blade's thickness. If you were to run your fingers down the flat of the blade from the hilt to the tip, you would feel it getting progressively thinner. The blade is thickest where it meets the crossguard, providing maximum strength at the point of greatest stress. From there, it thins in a smooth, continuous line all the way to the point. An Ulfberht blade might be 5 or 6 millimeters thick at the hilt, and only 2 or 3 millimeters thick near the tip. The sophisticated tapering does several things, like the fuller, it removes a significant amount of weight from the blade, especially from the outer half, but more importantly, it fundamentally changes the sword's handling dynamics. By concentrating the mass closer to the warrior's hand, the distal taper moves the sword's point of balance much closer to the hilt. A typical Ulfberht balances only a few inches in front of the crossguard. This balance point makes the sword feel much lighter than it actually is. It reduces the rotational inertia, meaning it takes much less wrist and arm strength to move the tip. The sword becomes incredibly responsive and maneuverable. The point can be guided with precision. It is not a clumsy, club-like weapon. It is a nuanced instrument of combat. The distal taper also affects how the sword behaves on impact. It helps to place the center of percussion, or sweet spot, in the optimal cutting portion of the blade. Hitting with this part of the blade transfers the maximum amount of energy to the target with a minimum of jarring vibration being sent back into the wielder's hand. To create a blade with a perfect double taper required a master's eye and hand. The smith had to control the thickness and width of the blade with every hammer blow, ensuring a smooth and even transition along its entire length. This wasn't just blacksmithing, it was sculpture. The elegant tapers of the Ulfberht blade were a secret hidden in plain sight, a subtle bit of engineering that transformed a simple weapon into a perfectly balanced extension of the warrior's will. Number 3, the hilt was an engine of balance. The blade of the Ulfberht sword was a marvel of metallurgy and engineering, but a blade alone is not a sword. The hilt, the crossguard, grip, and pommel was not just a handle. It was an integral part of the weapon system, a carefully designed engine of balance that completed the sword and made it work as intended. The construction of the hilt was the final piece of the physical puzzle. Let's look at the components. The tang, the narrow extension of the blade, passes through the crossguard and the grip. The crossguard, a simple bar of iron, served the obvious function of protecting the user's hand from an opponent's blade sliding down their own. The grip was typically made of wood, possibly covered in leather or wire, and provided a secure hold. But the most important part of the hilt, from a physics perspective, was the pommel. The pommel was a heavy, solid piece of iron, often with a distinctive lobed or triangular shape. It was attached to the end of the tang, usually by peening, which means the end of the tang was heated and hammered flat like a rivet, locking the entire hilt assembly together into a tight, solid unit. The pommel's most obvious job was to prevent the sword from slipping out of the user's hand, but its primary purpose was to act as a counterweight. The heavy pommel shifted the overall balance point of the sword backward, closer to the hand. As we saw with the distal taper, this makes the sword feel lighter and more agile. It allows the wielder to control the point with small movements of the wrist rather than large movements of the arm. It makes the sword a faster weapon, but the pommel does more than that. It fine-tunes the sword's rotational dynamics. A heavy pommel, by placing mass at the very end of the lever opposite the blade, makes the sword easier to pivot in the hand. This is crucial for the complex cuts, parries, and feints of a real sword fight. The weight and shape of the pommel and crossguard were not chosen at random. They were carefully matched to the weight and balance of the specific blade they were being fitted to. A smith would forge a blade, and then he would select or forge a pommel and guard that would make the completed sword balance at the perfect point. A slightly longer blade would require a slightly heavier pommel. A blade with a more aggressive distal taper might need a lighter one. The hilt was custom fitted to the blade to create a single, unified, and perfectly balanced weapon. When a warrior held a finished Ulfberht, he was holding a complete system. The high-tech crucible steel of the blade provided the strength and edge retention, the fuller and distal taper provided the lightness and stiffness, and the hilt assembly, especially the pommel, provided the balance and control that brought it all together. It was this holistic approach to design, where every part worked in concert with every other, that made the Ulfberht sword not just a piece of metal, but a true fighting machine. Number 2, the knowledge vanished with the trade routes. By the late 11th century, the production of the true crucible steel Ulfberht swords ceased. For centuries, this was seen as a great mystery, a case of lost technology. Or how could European smiths, who had been working with this incredible material for 200 years, simply forget how to do it? The answer is that they never knew how to do it in the first place. The European smiths were not the creators of the secret. They were the end users. The knowledge that vanished was not the knowledge of forging, but the access to the raw material. Let's look at the world around the year 1050. The political and economic landscape that had defined the Viking Age was changing rapidly. In the east, the Volga trade route, that great artery of commerce, was becoming choked. The Khazar Khaganate, which had policed the lower Volga, had been shattered by the Ruses a century earlier, creating a power vacuum. New waves of nomadic peoples, like the Pechenegs and the Cumans, were sweeping across the Eurasian steppe. They were disruptive forces, raiding trade caravans and making long-distance travel precarious. The flow of goods from Central Asia to Northern Europe, which had been relatively stable for 2 centuries, slowed to a trickle and then stopped. The supply of Wootz ingots from Merv and other eastern centers was cut off. The Ulfberht workshops on the Rhine, which had built their entire reputation on forging this exotic steel, could no longer get their hands on it. Their secret was not a technique they could teach an apprentice, it was a supply chain. They were master forgers, not master steelmakers. They knew how to take the strange crystalline cakes and turn them into peerless swords, but they had no idea how to make the cakes themselves. The process of making crucible steel with its sealed pots and high-temperature furnaces was a closely guarded secret of the artisans of Central Asia and India. At the same time, European steel technology, while still inferior to crucible steel, was slowly improving. The smiths were getting better at building larger and more efficient bloomery furnaces. They were developing techniques like water-powered hammers, which allowed them to work larger blooms and consolidate them more effectively. The quality of locally produced European steel was rising. While it could not match the slag-free purity and high carbon content of the Ulfberht blades, it was becoming good enough. A well-made 12th century European sword was a formidable weapon, a significant improvement over its 9th century ancestors. The disappearance of the Ulfberht was not a technological step backward, but a sideways shift driven by geopolitics and economics. The superior foreign material became unavailable, so smiths focused on improving the local material. The secrets of the Ulfberht were not forgotten in a library, they were lost on the steppes, in the chaos of a changing world. The swords themselves remain buried in graves and riverbeds as silent witnesses to a time when the world was, in some ways, more connected than the one that followed. Number 1, a modern blacksmith recreated the fire. For decades, the Ulfberht sword was a puzzle for academics and a legend for swordsmiths. We knew from scientific analysis what it was made of, but no one in the modern world had actually tried to recreate one using period-appropriate tools and techniques. That changed with a man named Rick Ferrer. Ferrer was a master blacksmith, a quiet, thoughtful craftsman with a deep respect for the skills of the past. He was not an academic, but a man who learned through the fire and the hammer. In the early 2000s, he was approached by the producers of a Nova documentary to do the impossible forge an Ulfberht sword. Ferrer's journey was a practical exploration of all the secrets of the Ulfberht. First, he needed the right material. He couldn't just order a bar of high-carbon steel. He had to start with a crucible steel ingot, just like the Frankish smiths did. He acquired a custom-made Wootz ingot, a small cake of steel made in the ancient way. His first challenge was the one the original smiths faced, breaking down the ingot's brittle, crystalline structure. His initial attempts failed. He heated the ingot and struck it, and it shattered into pieces. He had to learn through trial and error the exact temperature and the precise kind of light, rapid hammer blows needed to slowly coax the steel into a workable bar. It was a frustrating process that gave him a profound respect for the patience of his predecessors. Once he had a workable bar, he began the long process of forging the blade. Using only a charcoal forge, an anvil, and hammers, he drew the bar out, carefully creating the profile and distal tapers. He had to forge in the fuller, a task that required precision and control. Every step was a physical and mental challenge, a constant conversation between the smith, the steel, and the fire. He was not just following a set of instructions, he was rediscovering a lost language of craftsmanship. The most nerve-wracking part was the heat treatment. After weeks of forging, the entire project was on the line. He heated the blade to the critical temperature, judging the color by eye in his darkened workshop. He then plunged it into the quenching tank. He listened for the telltale ping of a crack, but the blade survived. It was now glass hard. Next came the tempering. He carefully polished the blade and gently heated it, watching, the colors run across the surface. He waited for that perfect straw brown hue and then let the blade cool. The final sword was then tested. It was put up against a typical Viking-era replica sword made of softer steel. In the test, the replica sword bent badly when striking a shield. Ferrer's Ulfberht replica cut cleanly and remained undamaged. In a sword-on-sword strike, the Ulfberht cut a deep notch into the softer blade, while its own edge suffered only microscopic chipping. It bent in a dramatic arc and sprang back to true. It performed exactly as the legends described. Rick Ferrer's work was a revelation. It proved that the Ulfberht sword was not a myth or a lucky accident. It was the result of a specific, difficult, and repeatable process. By recreating the fire, the sweat, and the stress, he brought the secrets of the Ulfberht out of the laboratory and back into the forge. He showed that the unmatched strength and flexibility of this ancient weapon came from a perfect storm of factors, an exotic, high-purity material from the East, and an incredible depth of skill and knowledge in the hands of a master craftsman on the Rhine. He closed the circle, connecting the modern world with the lost genius of the Viking Age.